3.2, differentiability. So how f prime a might fail to exist. Okay, so they're going to give you the possible examples of why f prime a, or the derivative of f at x equals to a, does not exist. Okay, all right. So number one, the first one is a corner. A corner. So it would be if I have something that looks like this. Yeah, we kind of talked about this yesterday. I mean, the other day, right? We said it's kind of a hinge here, and I really don't have any way to really set the slope here at the tangent line, right? If you look at if you view the derivative as the slope of the tangent line, right? I can't really set it. Okay. Same to the corner is what we call a cusp, which is kind of like a corner, but it's where two not lines, but curves meet, right? So this was a corner, whereas this is a cusp. Okay. So that's figure 3.12. Obviously the same thing here, right? Again, I have no way to anchor the slope here. I don't know what it is, okay? All right. Another one is a vertical tangent, So if I have a graph that looks like that, okay? If I'm looking at the tangent, slope of the tangent line, the slope of the tangent line becomes like this, and this is undefined, right? This is where you're taking a number and trying to divide it by 0. Undefined, so therefore, again, it is not differentiable here, okay? Because it's undefined. Because the slope is undefined there, right? Okay. And you don't want to confuse that with something that looks like this. If I have something like this, okay, I'm going to have the same situation. However, it's going to look like 0 here, and then it's going to go back up like this, right? It's going to go like that, okay? So here it becomes 0, which is okay. You can have a 0 slope, okay? So it's differentiable, and the derivative is going to be 0 at the origin. Mm-hmm. And then last but not least, on number 4, we have a discontinuity when it's discontinuous. Okay, it's again not differentiable. Okay. So let's kind of think about it, keep that in mind, right? So when it's discontinuous, there isn't going to be a derivative. Okay, all right, so let's kind of keep that in the back of our mind. Okay, so example number 1, find all points in the domain of that where f of x is not differentiable. Example 1, f of x is equal to minus 2 plus 3. So this is nothing more than we're taking this function, and how are we translating it? Because it was going to be here with a chevron that looks like this, right? But I'm going to move this where? 2 to the right or left?
Right.
2 to the right. And then 3 up or down?
Up.
Up. So it's going to look like this, right? So the point where it's going to be not differentiable is going to be right here, right? And why is it not differentiable? What is this called? It's a corner, right? Not a cusp, but a corner. It's a corner, right? This is a corner, okay? All right. So that's where it's going to be not differentiable. All right, in the middle of page 112, we have a thing that says differentiability implies local linearity, okay? Implies that locally, if you dial in and if you zoomed in close enough, every curve is going to look like a line once you zoom in so much, okay? And it's called local linearity, all right? Okay, so let's go to page 113. There's a numerical derivatives on a calculator. So there's a green box there that says the numerical derivative. Okay, the numerical derivative is found in this fashion in your calculator. Okay, this is what they're calculating. So they're calculating the slope. If you're trying to find the differential or the derivative at f, so what we're trying to find is this. And your calculator is going to do this. What it's going to do is going to take at any point on the graph, okay, it's going to go 0.001 this way and 0.001 this way. And they're going to take the 2 points and they're going to do the slope between those 2 points. Okay? So this basically is what? This is the same as, the way you got at this is a plus 0.001 minus a minus 0.001. That's how you come up with this, the length of these two, right? Because this guy here is this guy. This guy here is this guy. Okay, and that's where the 0.002 comes from. Okay, so this is how you do a numerical derivative. This is how your TI-84 works. Okay, this is what it's actually calculating when you ask it to calculate the derivative. Which at this point you should be saying, there's a way I can do this on my calculator? And you haven't told us that yet? Well, I'm about to tell it to you, okay? All right? And we will talk about that here soon. But anyway, this is how you do a derivative on your calculator. So let's look at page, example number 2. Let's do example number 2. Example number 2 says f is equal to x cubed. Use the numerical derivative to approximate f prime of 2. So it's going to be what? 2 plus 0.001 cubed minus 2 minus 0.001 cubed over 0.002. And this is what they're asking you to do. So if you do that, you're going to get 12. Okay? It's going to get 12. Okay? So let's go over to, this is also called the symmetric different quotient. This is called the symmetric difference quotient. Pretty long words here. Why is it symmetric? Because you're going 0.001 on one side and 0.001 further from the other side, right? So it's symmetric because you have the same difference there, right? It's the difference because you're calculating the difference between this guy and this guy. And it's the quotient because you're dividing it by 0.02. Symmetric difference quotient, okay? So where does this fall apart? Where does this fall apart? This falls apart in example number 3. Y is equal to that. If we do that, if you calculate, if you do this, what are you going to get? You're going to get this. So at zero, so let's say that, so f prime 0, we're trying to find f prime 0. So if I use a symmetric difference quotient, what am I going to get? I'm going to get 0 plus 0.001, and it's going to be the absolute value, because that's what it is. The function is the absolute value, minus, I'm going to go the other direction, over 0.002. So what do I get on top? Anybody tell me what I'm going to get on top? This is 0.001 minus, this is 0.001. So I get 0, right? So your calculator, if you put this in and ask it to do the derivative at 0, it's going to come out and say the derivative is 0. Okay. When you and I just talked about this, and we said that what a 0, it's a corner, so the derivative does not exist. Again, the calculator is only as good as the user. Okay? Now, that being said, the actual function that you are going to use is called ender. Ender, and I think in the, I think it's FNDER for the 84. Is that correct? In your calculators, it's FNDER?
Mine says n deriv.
N deriv, okay, N deriv, okay, N deriv. Like that? N deriv?
Yeah.
Okay, so ender or n deriv, okay, this is, if you look at the function, okay, if you look at how to use that, okay, what does it say? What is the actual, when you display, when you put that in, what does it ask for? It asks for the actual function, correct? Asks for the actual function. And it asks what is the variable. And it asks the point, I believe. Are those the 3 things that they ask on the end deriv?
I believe so, yes.
How do you get to the end deriv?
Yeah, end deriv.
How do you get to it?
It's in math.
The math.
Math.
Yeah, number 8.
Ah, I see.
Okay, so you have to input these 3 things. You have to tell it what your function is. This is the actual function itself. This is the variable. And this is the point where you want to find it. I think, right? Does this work?
I'm
The
giving like a
is the first.
Put this in, what do you get? X squared, y, f is, I want to find the derivative at x equals to 1 for x squared.
Says 2.
2, which is correct. Okay, so when x equals to 1, the derivative of x squared is equal to 2. Okay.
The first one it asks you is just x. So the first one is the variable.
Oh, the first one is a variable, so I got this switched.
Yeah.
Like that? Okay.
Yep.
All right. You can tell that I'm not a calculator guy, obviously. For those who haven't figured that out yet. Okay, so that is the ender, how to use the ender. Okay, now remember what I thought we said, okay, so if you have a derivative, okay, it means that there is a local linearity, which also means what? It has to be continuous, correct? You cannot have local linearity with it being discontinuous there, right? So on page 115, it says differentiability implies continuity, okay? So in the middle there, it says theorem number 1, differentiability implies continuity. If f has a derivative at x equals to a, then f is continuous at x equals to a. Okay. And then for last but not least, we are going to learn the IVT for derivatives. Okay, we already had the intermediate value theorem once, right? We said that in a function that looks like this between A and B in the closed boundary here, you are going to be, this is going to be f of A, and this is obviously going to be f of B. If it is a continuous function between A and B, it has to go through all values of f of A and f of B, all right? In other words, y-wise, you have to go through all of the values between these two. You cannot skip any. You will, at one point, you will have to go through one of these values. Okay, all right. The IVT for the derivatives say what? If A and B are 2 points in the interval in which f is differentiable, then f takes on every value, f prime takes on every value of, so it's the same situation. Now we're saying that not the f of x is going to take on these values. What we're going to say is the f prime x is going to take on all values between f prime a and f prime b. Okay? And that is the IVT for derivatives. So that's number 2. Okay, number 1 was the intermediate value theorem, which was just a regular between A and B. F of x is going to take on f values between f of a and f of b. Okay, this is for the derivatives. So in the derivatives, it's saying between A and B, f prime x will take on all values between f prime A and f prime B. Okay. All right. That's it. And we're done with 3.2. Are there any questions that I can answer that you can think of at